Hello, my name is Amin Misaghi Bonabi. I'm a PhD candidate at Delft University of Technology, and today I will present our work on comparative analysis of CO₂ and H2 plume migration in aquifers. This research has been carried out in collaboration with my colleagues Willemijn van Rooyen, Mohamed Al-Kobaisi, Kees Wouk, and Hadi Haji Begi. The concept of utilizing geological reservoirs for a sustainable future has existed for a long time. For decades, geological carbon dioxide storage has been studied intensively. In contrast, underground hydrogen storage has only recently attracted attention. Although the purpose and implementation of CO₂ storage and hydrogen storage are different, our attempt is to bridge the two topics, to transfer knowledge from CO₂ to hydrogen, compare their plume migration and trapping mechanisms, and build confidence in UHS studies. We modeled CO₂ and H2 with different equations of the state to capture their thermophysical properties. For CO₂, we used modified Redlich-Kwong equation of the state, and for hydrogen, we applied the Peng-Robinson US with the volume shift correction, which is validated against molecular dynamic data. CO₂ has a density 2 orders of magnitude higher than hydrogen. In reservoir condition, it is compared to the density of water. Both CO₂ and H2 reach a supercritical state in reservoir conditions, but CO₂ exhibits a jump in density and viscosity, whereas for hydrogen it continues the same pattern. Hydrogen also has low dissolution. As a rule of thumb, the dissolution of hydrogen in reservoir conditions is in the range of the dissolution of CO₂ in standard conditions. We began with the fluid flow benchmark study under standard conditions of 1 bar and 20 degrees Celsius. It's a 2D layered system composed of 7 different soil types, including low permeability barriers to mimic caprock. The setup measures about 1.5 meters in height and 2.9 meters in length, with an open water layer on top and 2 injection wells at the bottom for gas injection. In this case, both CO₂ and H2 show broadly similar saturation patterns, but their plume migration is very different. The H2 plume spreads farther and occupies a larger region, especially in the upper layers, because hydrogen remains mostly in gas phase. CO₂, with a solubility about 75 times higher at these conditions, dissolves extensively into the brine, which limits the size of its gas plume and creates continuous dissolution, particularly in the upper regions where fingerings develop. In contrast, H2 does not exhibit fingering. It quickly reaches a steady state with dissolved hydrogen remaining at the same place. Due to higher pressure buildup, the H2 plume can even overcome low permeability barriers, while the CO₂ plume remains more contained. The second case scales the fluid flow setup to realistic reservoir conditions of 150 bar and 50 degrees Celsius. The model represents an aquifer about 1.3 km deep and 2.9 km long with anisotropic permeabilities and 2 caprock layers. 2 wells inject CO₂ and H2 at equal volumetric rates over several months. At reservoir conditions, the plume behavior of CO₂ and H2 diverges much more strongly because of their density contrast. CO₂, being denser, spreads more evenly in all directions, while hydrogen rises rapidly and accumulates beneath the caprock. For example, CO₂ takes over 5 years to reach P3 reference point, whereas hydrogen gets there in only a few months. Hydrogen also penetrates deeper into the caprock and stabilizes much sooner than CO₂. Unlike CO₂, which shows fingering due to dissolution, hydrogen exhibits no fingering, which is in this case actually beneficial because it reduces solubility losses. In this presentation, I highlighted the results from the standard and reservoir condition cases. In our paper, we also extend the analysis to cyclic storage scenarios. I invite you to read the paper for those additional results and practical insights.